As a journalist, I'm kind of on a parallel track with you folks. I may not do sort of, skeptical type debunking like we heard before, but, as a science writer, you face a kind of challenge that, say, a sports writer wouldn't. A sports writer does not have to think about whether some of his readers don't think that basketball even exists. And when I started writing about science in the 1990s, working at Discover magazine, one of my main focuses was evolution, because it's amazing and cool. But I knew that there were a lot of people who were either actively in active opposition or just couldn't imagine that life as we know it could evolve. And so I would look for the stories that would, where I could talk about advances in science and then also help people to overcome those doubts. And so my first book 20 years ago, At the Water's Edge, focused on one of these particularly contentious things of big transitions in evolution. For example, how do you get a whale? I mean, it's a mammal. Darwin said that it could go into the ocean. At the time, Darwin didn't have any transitional fossils. And so, creation said this could not possibly have happened. You could not possibly have a whale with legs. And I was lucky enough to be reporting at a time when exactly that was discovered. This is 47 million years old. This is what it would look like in real life. Literally a whale with legs. An amphibious whale with legs. And we know it's a whale because of the certain traits in its skull. And we actually have found, we being incredible paleontologists doing years of hard work, they have found lots of whales with legs. And this is a tree that I put together with Doug Emlin in a textbook, which is a super, super simplified tree. We just picked a few of the many branches that there are. There are actually dozens of species of intermediate whales with legs, and you can see how the whale body has emerged. You can see it. And that's what I try to do as a journalist is to look for these particularly great stories. So you get mail when you write about things like this. So this is, one example. You can be sure of this, Carl. The reason you cannot see how wrong you are is that the God of this world, Satan, has blinded your eyes to the truth. May God have mercy on your soul in Christ, Bill. I don't know Bill's last name. I guess he thought we were on a first name basis. But in any case, writing about evolution, I sort of felt like I was kind of getting the brunt of this at first, compared to my colleagues. But unfortunately, in my time as a science writer, I've seen other topics that were once just not the subject of controversy become controversial. So vaccines in the 90s wasn't really a thing. Now it's a thing. Now we have outbreaks and deaths because there are people who are suspicious of vaccines, hesitate to give it to their kids. There's real damage being done now. And climate change, honestly, in the 1990s, we would report on the science of climate change, and we didn't get any hate mail at all. You put something on the web now about climate change, and you just have to, put up your shield because you're going to get pelted with very well-organized denialism. And I think it's great that skeptics are fighting the good fight on these fronts. I would actually suggest that now there's actually a new thing that you should add to your portfolio, and that's the subject of my latest book, which is heredity. There's actually a lot of misconceptions about heredity, and they can be quite powerful because they're misconceptions that really go to how people define themselves. Because a lot of the way we define ourselves has to do with how we look at heredity, the link between ourselves and our ancestors and the past. And people are thinking about heredity right now more than ever. Now, of course, people have been thinking about heredity and telling stories about heredity for a very, very, very long time, long before anybody knew about genes, DNA, and the rest. The word hereditas comes from, is the Latin word where heredity comes from. It didn't refer to genetics or anything like it, or why you look like your parents. It had to do with the rules for inheriting stuff. And so in order to inherit stuff and power, you actually had to have a good proof of who your ancestors were. And that's where genealogy came from. This is a family tree in the Middle Ages, where Edward IV is in effect showing you why he gets to be king. Looking at his ancestry, he inherits the throne. And then this sort of starts to develop into a language of what it is that connects you biologically to your ancestors. Blood, royal blood, noble blood, pure blood. And if two people come from different places, they were started to be defined as different races. And if they had a child, that child was a quote-unquote half-blood. We'd slice it down to terms going down to like a 64th of this mythical blood. Now, of course, in the late 19th century, a number of scientists made advances in cell biology and also rediscovered the work of Gregor Mendel, and they realized that there were actually these heritable factors, that's what they would call them, in cells, and that was the basis of biological heredity, not some mythical blood. And it was really a very exciting moment in 1900. William Bateson actually coined the name genetics for this brand new science. And literally, just as he is inventing this new science, he declares the whole problem of heredity has undergone a complete revolution. It's almost like you feel like, well, we're just about done here. We got it all worked out. There was a lot of hubris going into this. And the irony is that if you wanted to understand human heredity, nobody knew about DNA. No one would be able to do breeding experiments like Mendel did on people. So what would you do? Well, you would adapt the genealogy of old. So Charles Davenport, Cold Spring, of what is now the Cold Spring Harbor Laboratory, started working on pedigrees, family pedigrees, and looking for diseases and how they were passed down through the generations. And some of this was incredibly important work, and it's still the way that a lot of hereditary diseases are studied now. Look at the family, see how the disease gets passed down. But Davenport really ran with this. He once made a tree about boat building, because there was some family where boat building seemed to run in the family, so therefore there must be a boat building gene. This, in my book, I talk about how this kind of reached extreme and really destructive proportions when Davenport wrote to the Vineland Training School, which was a place for the quote-unquote feeble-minded, to ask if they had done any research on the heredity of feeble-mindedness. And it just so happened that the psychologist at the school, Henry Goddard, had just discovered the Binet intelligence test and was actually introducing intelligence testing to the United States. He introduced it into public schools to identify people who need special education. Eventually, he would go on to use it on the Army. So basically, American intelligence testing is due to Henry Goddard. So Goddard starts to investigate hundreds of his students and sending out field workers, trying to find families and get stories about ancestors and see if they're feeble-minded. This is the term they used. And to be classified as feeble-minded, you could do a lot of stuff and be called feeble-minded. You could steal a horse. You could drink a lot. You could get paid off to vote twice. You're feeble-minded. And so he would create these trees, and his favorite tree, the one that he actually publicized in a book called the Cowlick Act Family, had to do with one student named Emma Wolverton, who was not actually feeble-minded. She was just inconvenient. Her family wanted to essentially get rid of her, and so they said she's trouble at school, and the training school said, yeah, okay, she's feeble-minded. And she spent the rest of her life institutionalized. She was not alone. This happened to a lot of inconvenient girls. So Goddard sends out a field worker who comes back with this amazing story. And you can see the tree there. At the center there's an N, kind of where the two branches branch off. And that is one of her ancestors, who Goddard calls Martin Cowlick. And Cowlick gets drunk and sleeps one night with the woman who's represented by the black F there. And if it's a little hard for you to read the words, it is the nameless feeble-minded girl. So he sleeps with a nameless feeble-minded girl who then produces a long line of feeble-minded people, ending with Emma, who is called Deborah Cowlick in this book, The Cowlick Act Family. Then he sobers up, finds an upstanding woman. That N with a circle is called the lawful wife. And they have a long line of totally upstanding members of society. Now, this actually was a complete botch. This is fake. This is not real. It turns out that father and son there, the feeble-minded son, they were not father and son. They were like fourth cousins. And all those things people marked as F were not, in fact, feeble-minded. They were farmers. They were soldiers. They were car salesmen. I mean, it was all a big botch, a complete fiction. And yet, Goddard was really high on this. He said, the biologist could hardly plan and carry out a more rigid experiment. And he said this information that he was producing from Vineland, quote, was among the most valuable that have ever been contributed to the subject of human heredity. So you can see he kind of thought, like, there's Mendel, and then there's me. And you might think, oh, well, this would have just gone nowhere. But no, it was a huge bestseller. It was incredibly influential culturally. This is one editorial about it. And the concern was, well, gee, all these people have these genes for feeble-mindedness, and they're having kids. We got to stop this. And so this fed into the growing movement of American eugenics. And what that led to is that Goddard, Davenport, and other scientists lobbied for sterilization laws around the United States. Those laws were passed and led to tens of thousands of people being sterilized in the United States. Goddard was asked to help develop immigration policy. His testing led him to conclude that half or more than half of all the Russians, all the Jews, all the Italians coming to the country were feeble-minded. So that's one of the reasons why the quotas were put in place in the 1920s. There were people who looked with great admiration in other countries at what we were doing in the United States. Not surprisingly, Germany. And so if you went to a movie in the 1930s, you might get a little educational film. This is called Heredity in German. It's German for heredity. You can actually find it on YouTube. And it starts with a scientist explaining some of the basics of the birds and the bees. And then when they turn to humans, this is what they show. That the Cowlick Act family is proof that feeble-mindedness is hereditary, and therefore, the only thing we can do is stop it, and stop it not just with sterilization, but extermination. So I think that today, it's worth bearing in mind just how leading scientists could go really off the rails and use old-fashioned notions and biases, allow those to influence their science and the conclusions they draw about it, especially about heredity. And I think we really are in the real revolution now, because DNA sequencing and analysis has exploded. I mean, I'm writing about things as a journalist now I never would have imagined that I could be doing. And not only that, but everybody seems to be getting their genes tested, which is also extraordinary. This is an article from Wired talking about how Ancestry's genetic test was among one of the most popular gifts last Christmas. There was a Super Bowl ad for 23andMe. So, I mean, if there's any measure of making it into popular culture in America, I think a Super Bowl ad is that. And just look at the numbers. This exponential curve is impressive, but also like look at the years. I'm not starting in like 1900. I'm starting in 2014 here. And this graph only goes halfway through 2018. So there might be 100 million people by 2020 who have gotten their DNA tested. That's amazing. It could be an incredible scientific resource, but it's also going to mean that lots of people are going to be looking at their results, trying to say, what did I inherit? How did my ancestors make me who I am? And I have a piece coming out in the Sunday Review in the New York Times this weekend. It's online now, so you can check it out. But this is dangerous terrain because people make a lot of assumptions based on old ideas like blood when they look at these results. And there are a lot of misconceptions that can lead people astray. And especially when they're looking for things like their ancestry. So, for example, misconception number 1. How many people have bragged about being descended from somebody famous? I think a variant of, my mother is a big genealogist, and she discovered that the closest thing I have to a famous ancestor is John Howland, who is famous. He was on the Mayflower. That's not why he's famous. He's famous because he fell out of the Mayflower. He got, someone threw him a rope. He survived. I suppose if they hadn't thrown that rope, I wouldn't be here. I don't know. Anyway, it's kind of amusing that I can draw a straight line back to John Howland on my mother's side. So I wrote the book, and I mentioned that in the book, and I got an email from someone who was so excited, so excited. She said, "I am also descended from John Howland. Oh my gosh, we are descended from John Howland." And I don't know how to break it to her, but someone actually did sort of some back of the envelope calculations about John Howland. I don't know why, but it turns out there are 2 million people descended from John Howland in the United States. So if you're descended from someone special, that doesn't make you special, because lots of people are descended from people a long time ago. In fact, there's something very weird. The further back you go, the more likely it is you are descended from someone special. If people with European ancestry alive today are more than likely directly descended from Charlemagne. Congratulations. It's just the nature of genealogy. If you go back even further, just a few thousand more years, anybody who alive then, about 5,000, 6,000 years ago, who has a living descendant today, is probably the common ancestor of everyone on Earth today. So again, we should look at genealogy as actually bringing us together rather than separating us into special categories. There's this, John Howland. I'm a direct descendant of John Howland, so surely there must be a little John Howland gene in there, right? Because he helps to make me who I am, right? Wrong. That's not how it works. Blood might be infinitely divisible, but DNA is not. It gets shuffled and sorted with every generation, and you can end up with not getting any DNA from an ancestor at all. And actually, Graham Coop from Davis has done some calculations, and basically this shows you that it really starts to fall off at about 8 generations or so. And then, by the time you're down at 12, 14 generations, if you pick any one ancestor, you probably don't have any DNA from them at all. You just have a sampling of DNA from your ancestors. They're still your ancestors. It's just that genetics doesn't equal genealogy, as Graham Coop says. There's a gene for every trait that you inherit. Like there's, a gene for being tall, for example. Well, Joel Hirschhorn went and looked for genes for common gene variants for height. This is showing how he found one in 2007 called HMGA2. That little spike there shows you that there's something interesting going on in this gene. We have no idea what this gene really does when it comes to height. This is what happened when it's broken, as opposed to just slightly mutated. But the fact is that HMGA2 only affects you by about 1/8 of an inch. So why some of us are taller and shorter, that actually only tells a very small part of the story. And actually, if you look at the science that Hirschhorn and others have done since then, we're now up to 3,290 genetic variants linked to height. And that probably is going to go up. It's even possible that our whole genome might be influencing our height. It's kind of a weird way of thinking about it. But we have to move beyond the sort of one gene, one trait kind of thinking about who we are. There are some cases where that's true, but most of the time that's not true. Finally, genes don't matter because epigenetics. Epigenetics has, for some reason, become the ultimate woo. This is not about your genes, but the molecules around your genes that turn them on and off. And when a cell divides, those new cells don't just inherit genes, they inherit the molecules around the genes too. So epigenetics is worth thinking about, but it's not the reason that it's not like your grandparents having trauma is why your life isn't working out quite the way you wanted and you have to go to therapy. This is actually a book that makes that claim. This is not true. On the other hand, as skeptics, you should not throw the baby out with the bathwater. Epigenetics is important, and it could be a very important kind of heredity. It's certainly true for plants, might be true for some animals. Whether it's true for humans, there isn't really good, strong evidence. So we can't rule it out, but when all these people are jumping to basically charging you, $300 for a epigenetics trauma workshop to cure what ails you, buyer beware. And that sort of openness to possibilities, it really does extend to other kinds of heredity. Maybe epigenetics is a separate channel of heredity. There are many anthropologists who argue that culture itself represents another channel of heredity unique to us. We have a special kind of heredity culture, which scientific thinking is one of the products of that. You could not just, drop down in the middle of the Arctic and figure out just on your own how to survive. These people have inherited knowledge and practices and traditions for thousands of years, and that is just as important as, a gene that might make them better able to withstand the cold. So, finally, I just want to say that, we should be thinking about heredity in this skeptical way, in this careful way, not just because of what we get on a 23andMe report and wanting to make proper sense of it, but also because we're at the point where we're on the verge of being able to manipulate heredity in the future. So that we have these inherited disorders like Duchenne's muscular dystrophy, fatal diseases, with no cure right now. And we see, these headlines about how CRISPR is perhaps making it possible to edit these mutations out, cure these diseases from birth, and then these diseases are not carried down onto future generations. This is a profound moment, and we have to really think about, what is it we mean about heredity, and what is the kind of heredity that we want to step in and stop versus what do we want to let move forward? I mean, that was the decision that eugenicists wanted to make. I think that most people are okay with saying, well, let's just edit out Duchenne's muscular dystrophy. And you could, in theory, do that. But what about other cases? So there's a condition called Larren Syndrome, which is a condition where people grow to be quite short. And this is actually a case where there is just one gene. It's a gene for a growth hormone receptor, and there's one mutation, and it causes this. And this is a group of people in Ecuador known as the pimientos, just a few hundred of them, and they inherit this condition. There are people who feel that being very, very short is a disorder. Parents will give their kids growth hormone to get them to be proper height, proper in quotes. So should we edit out that mutation? The fact is actually that people with Larren Syndrome are quite healthy. They're healthier than all of you. They have very low rates of chronic diseases like diabetes and cancer. And it probably has something to do with they're not using so much growth hormone. So if you judge them as being undesirable in one way, you're ignoring other aspects of them. And really, ultimately, we have to remember that we're talking about human beings, and that just this attitude of looking at people as being the sum of the genes that they inherit can be quite dehumanizing. Emma Wolverton was a victim of this. Became famous as being, a feeble-minded girl who was doomed to a life of feeble-mindedness by her heredity, and died in an institution because of that. So I would just say, let's try to bring skepticism and care to understanding of heredity in honor of Emma Wolverton. Thank you very much.
Thanks for watching. If you liked this video, be sure to give it a thumbs up and share it with your friends. Don't forget to subscribe to the channel and ring that bell to be notified about new videos. You can follow us on social media, and if you really love what we do, consider supporting us with a donation. Links to all that good stuff is in the description below.